Oh. No. All right, so let's go ahead and get started today. So today's class is on different forms of representing logic. So I have the various topics that we're going to cover in class, and it's probably going to take a little over an hour. And if it does, we'll take a break at the top of the hour or close to the top of the hour. And then once we're done with the lecture, there's an activity that I have for you. And again, just like all the activities, I'll supply the answers, and the answers to the activities right up there on the right side of the whiteboard. And then once you're done with the activity, you should have time at the end of today's session to work on the lab 0. I'll tell you the second part of it. And remember, that lab is due Friday of next week, okay, on the 19th. All right, so everybody should have a handout, okay, a handout that looks like this. If you don't have it, let me know, because I have some up here. I can give you one. You don't have one? Okay, anyone else need one? So on this handout, it has 3 of the logic gates that we're going to talk about. And then also, there's an additional 2 gates that aren't on this handout that we'll talk about. And then you can also see below where the symbols for the logic gates are with their truth tables, there's a bunch of different axioms and theorems. And these axioms and theorems are part of Boolean algebra. And Boolean algebra is just base 2 algebra, okay? In fact, if you look at some of these laws, you'll see that some of them are the same as what you have in base 10, like, things like factoring and things like that. But there are other laws and axioms that are unique to base 2 algebra. One of them called De Morgan's. We're going to spend some time on today's class. We're not going to go over all the different laws and axioms today. This handout is more of a reference sheet, okay, that as we go through the quarter, you'll see that this will, be a handy handout, okay? But where we're going to start today is the various logic gates. And the first logic gate we're going to talk about is the NOT gate, okay, which is also called an inverter. And the NOT gate has this logic symbol. Okay, it's an arrow with a little bubble, little circle on the point of the arrow. This is the input side. And this is the output. And often with logic symbols, we'll identify inputs and outputs with variables. So for example, we could use the variable A for the input. And if we did use A for the input of the NOT gate, the output would be shown like this. It would be shown with the same variable as the input, but then with a bar over it. And that's because in Boolean algebra, and again, Boolean algebra just means base 2 algebra. Base 2 algebra. In Boolean algebra, the bar over variable, it means opposite of. And in base 2 algebra, like we talked about last time, when you have a digital system that's binary, it only has 2 possible values, either a 0 or a 1. So with a NOT gate, if you put a 0 in, you're going to get the opposite, which is a 1. And if you put a 1 in, you'll get the opposite, which is a 0. So each of these logic gates have what we call a truth table. And the truth table shows you how the output relates to the input or inputs when there's more than one input. So the truth table for this NOT gate would just be that when input A is on 0, output NOT A is going to be a 1. If input A is a 1, output NOT A is going to be a 0. Okay, so that's the NOT gate. Does anyone have a question about the NOT gate before we move on to the next gate? All right. Okay, the next gate we're going to talk about is the AND gate. Okay, the AND gate has this symbol. Okay, this is a 2-input AND gate. You can also have 3-input AND gate, 4-input, 8-input, 16-input, 32-input. I mean, you can have as many inputs as you want on an AND gate. Okay, but the most standard is a 2-input like this one. The Boolean expression for an AND gate looks like this. Okay, this dot means AND. Also sometimes, and in fact, most of the time, people neglect the dot and just put AB like that, and it's understood that it's ANDed together. There's like an imaginary dot there. Okay. And what the AND gate function means, we can see in its truth table. So when you draw a truth table, by convention, the inputs go on the left side and the output goes on the right side. So since this is a 2-input AND gate, and both inputs can either be a 0 or a 1, okay? Each input is a bit, like we talked about last time. So since I have 2 inputs that can either be a 0 or a 1, how many unique combinations of 0s and 1s can I have? 4. How'd you get that? It's correct. How'd you get it?
Two of each. That's how you say, 2 squared.
Yeah, exactly. Yeah, because remember, this relation we talked about last time, that the number of values that you can get from a certain number of bits, its values equals 2 to the number of bits. Right? So if you have 2 inputs, meaning that you have a total of 2 bits, you can have 4 unique combinations because both bits could both be 0 at the same time, or this could be 0 and this could be 1 at the same time. This could be 1 and that could be 0 at the same time, or they both could be 1 at the same time. Okay. Now, an AND gate will only give you a 1 out when all inputs are equal to 1. Okay, if at least one input is a 0, you're going to get a 0 out of an AND gate. So you see, the output for the AND gate is going to look like this. Okay, you only get a 1 out when both inputs are 1. And again, this is true whether you got 2 inputs, 3 inputs, 4 inputs. You know, no matter how many inputs, all the inputs would have to be 1 to get a 1 out. Only takes 1 0 at the input of an AND gate to get a 0 out. Okay. So any question on the AND gates? All right, the next gate is the OR gate. Okay, the OR gate has this symbol. So you see the OR gate has like a curve on the input side where the AND gate has a vertical line. And the Boolean algebra for an OR function is we use the plus sign. Okay, so you see in base 2, right, Boolean algebra, that plus doesn't mean add like it does in page 10. That plus means OR. Okay, so you would say that A is ORed with B. Okay, and the truth table looks like that. In OR gate, you'll get a 1 out as long as at least one of the inputs is a 1. You only get a 0 out when all the inputs are 0. So it would look like this. Okay, so those are the 3 gates that are on that handout. Now, I want to talk about 2 other gates that are not on the handout. And the first of those gates is the NAND gate. Okay, NAND is short for not AND. And you'll see why it's called not AND. Okay, here's the logic symbol for NAND. Okay, so compare that logic symbol for the NAND to the logic symbol for the AND. Do you see the difference? What's the difference?
The little circle.
Yeah, there's a little circle on the output for the NAND. And you see the reason for that is because a NAND is the same as taking an AND and putting an inverter on the output. The NAND's the same as an AND with an inverted output. So, you know, this is kind of shorthand for that, right? It's like they're taking the arrow and squishing it into here and just leaving the little bubble showing to indicate that that's an inverted output. Okay? Now, the Boolean algebra is the Boolean algebra for an AND. Let's do this. Okay, the way you come up with it is, well, first A and B are ANDed together. Right, so you see at the output of this AND gate, it's just gonna be like what we have here, A ANDed with B, but then this whole thing is knotted. Right, so you see that would be the Boolean expression for a NAND, right? A and B are ANDed together, and then the whole thing is knotted. Okay, so the truth table okay, so the truth table for an AND, you'll only get a 0 out when all the inputs are 1, otherwise you get a 1 out. So when you compare the truth table of an AND to an AND, it's just the outputs are all inverted. And again, that's due to that inverter that's on the output. Okay? All right, so what gate do you think is coming next? NOR, exactly. Just like there's a not in, there's a not or. Okay, so we have a NOR. Has this symbol. Equivalent to an OR gate with an inverted output. An expression for an OR is that your inputs are ORed together and then the whole thing is knotted. So you have like A or B here. And here you're gonna have. Okay, and then the truth table. Okay, well, the output of the NOR is just gonna be, the outputs of the OR inverted, so. You'll get a 0 out of a NOR as long as one of the inputs, at least one of the inputs is a 1. And you only get a 1 out when all the inputs are 0. So it'd be 1 and then 0, 0, 0. Okay? So any questions on any of these gates? These 5 gates are called the basic logic gates. In a few classes, I think not next class or the class after that, we'll talk about a couple of other logic gates, okay, that, you know, aren't part of the basic gates, but they're still, you know, useful gates. Okay, but these are the 5, you know, basic gates, basic logic gates. Okay, so, oh, one other thing I wanted to show you was on that same handout, right, the one that has the gates and the laws and the axioms that, you know, we talked about at the very beginnings. Well, if you flip it around, it has a circuit diagram. Now, how many people have had like a circuits class? Okay, quite a few. Okay, well, if you haven't had a circuit class, don't worry. You know, nothing I test you on has to do with circuits. But I used to teach circuits quite a lot. And I like to sometimes mention some circuits, things that, you know, has to do with this class. So just so you can see how the different classes tie together. And this diagram here, this is a circuit diagram of a 2-input NAND gate. So this symbol, that NAND gate symbol represents a circuit like this. You know, this isn't the only way you can make a 2-input NAND gate. There's other circuitry that you can do, but this is a way to do it. And you can see there's a transistor, a couple of diodes, and a couple of resistors. So, you know, sometimes when you're dealing with these symbols, everything can kind of seem abstract and kind of magical, you know? But these symbols represent actual circuits that you can build, tangible circuits that you can build. Okay? Also, you know, the zeros and ones that we're using in the truth tables, those are shorthand for voltages. Ideally, a 0 is exactly 0 volts most often. Ideally, a 1 is 5 volts, you know, most often. But how many of you have actually made a voltage measurement with a voltmeter? Like in a lab or even at home or something like that? When you make a voltage measurement, you know, with a voltmeter and you look at the display, is that display nice and steady all the time or does it fluctuate? Yeah, it fluctuates over time, right? So these are ideal values, but in actuality, because voltage varies, we'll say that a 0 is equal to a voltage that's below a certain amount, like say 1.4 volts. And we'll say a 1 is equal to a voltage that's above that same amount. We call this a threshold voltage. Right? So as long as, you know, voltage is below that amount, it's going to be read as a 0. Voltage is above that amount, it's going to be read as a 1. Okay. So anyway, I just mentioned some of the circuit stuff, like I said, just to hopefully see how your classes, you know, relate somewhat. Right? Okay, so we talked about logic gates, talked about how these symbols represent electronic circuits. The next thing to talk about is De Morgan. Okay, so De Morgan's is one of the Boolean algebra laws. Okay, it's one of the more important ones. And there's two parts to De Morgan's. One part of it is a NAND gate is equal to, I gotta move the camera. Move my camera. Yeah, you'll notice I always write on the whiteboard to move the camera, because if I don't, I forget. But even sometimes, even though it's written there in red, and you would think, how can anyone miss it? I miss it. So if you ever see me not move the camera when I get to that point, please tell me. Okay, that's good. Yeah. Okay, so one part of De Morgan's is that a NAND is the same as an OR with inverted inputs. Or with NOTs on the input. Okay. The other part of De Morgan, so De Morgan has two parts. The other second part of De Morgan tells us that a NOR is the same as an AND with inverted input. So this is a NOR and equal to an AND with inverted inputs. Okay, now I'm just telling you what De Morgan's is at this point. We're going to come back to this when we get to SOP and POS Boolean equations. Okay, so we're gonna come back to this, but the next thing I want to show you is a truth table. Now, you know, we have truth tables for the logic gates to show how those logic gates function. But we also have truth tables that describe logic circuitry, you know, gates that are all interconnected. So in order to show you this, I have this example. Okay, so this is a truth table example. Okay, and in this truth table, we're going to have three inputs, C, G, and S. And we got one output E. And here, C stands for chips, like tortilla chips. G stands for eggs. And S stands for salsa. And E stands for eat. Okay, so we're gonna make a truth table based on my appetite for these ingredients, various combinations. Okay, and you know, we either have the ingredient or we don't have it, right? If we don't have it, it's a 0. If we have it, it's a 1. And then the output eat, well, if I'll eat that combination, it's a 1. If I won't eat that combination, it's a 0. Okay, so since I have 3 inputs that can either be 0 or 1, how many unique combinations do I have? 8. How'd you get it?
The third power.
Yeah, exactly. It's this again. Right? And remember, anytime you want to find how many values, how many combinations of zeros and ones you can get from a certain number of bits, it's just 2 to the number of bits. Right? So 2 to the 3, 8. Okay, so all 3 of these could be 0. Or we could have 0, 0, 1, or 0, 1, 0, or 0, 1, 1, or 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right, and then just make sure 2, 4, 6, 8. And anytime you're making a truth table like this, always put your inputs in binary order. See, if this, you know, if we treat these as a binary number, see, I'm just counting in binary here. I'm starting with 0, then 1, then 2, then 3, then 4, then 5, then 6, then 7. Okay, if for nothing else, it makes it easier for the grader when a grader is grading a truth table. If you mix them all up, it's harder to grade. Okay. All right, well, let's fill in output E. Now, again, this is based on my appetite. You know, your truth table, you know, might look different, but this truth table is based on my appetite. Now, no matter whose truth table it is, the first row is going to be the same, right? Because if you don't have any chips and you don't have any eggs and you don't have a salsa, you're not eating. There's nothing to eat. So this would be a 0. Okay, just salsa. I'm not a fan of just eating salsa out of the jar. Maybe some people are, but that's not me. So I'm not going to eat just salsa. Just eggs. Yes, I love eggs. Eggs and salsa, one of my favorite things. Salsa on the eggs is so good. How many people like salsa on their eggs? Like scrambled eggs? Yeah. If you've never tried it, It's really good. I like salsa on eggs. Just tortilla chips, sure. Chips and salsa, of course. Chips and eggs, not a fan. And not a fan of adding chips with my egg and salsa. Okay, so see where there's a 0, I wouldn't eat that combination. Where there's 1s, I would eat it. Okay, so you see the truth table represents a logic function, right? Because it's either you have it or you don't, right? Anytime it's have it or you don't have it, that's binary, that's logic. All right, so the next thing is we're now going to write 2 different forms of Boolean expressions or equations, starting with SOP. SOP stands for sum of products. Okay, you're going to see where that name comes from coming up here. And I'm going to write an SOP for output E. Okay, so E means when E is one. So this is gonna be an SOP, sum of products equation for the combinations of ingredients that I would eat. Okay, you'll see later, I'll write an SOP for not E. And an SOP for not E will show the combination of ingredients that I would not eat. Okay? All right, so the way I come up with an SOP for E is I just look at the rows of the truth table where E is a one, right? So starting with this, this row right here, where there's no chips, there are eggs, but there's no salsa. Well, the way I write that as a Boolean term is that any input that's a zero, I put a not, I put a bar over that variable because that means I don't have it. Anywhere there's a one, I leave that as the variable. If there's not a bar over it, that means I do have it since it's a one. Okay, so you see the term for this combination here would be not C because I don't have any chips, G because I have eggs, and not S because I don't have any salsa, right? I'll eat just eggs. Or I will eat this combination where I have eggs and salsa, but no chips. So you see, no chips, have eggs, have salsa. Or I'll eat this combination that is just chips. Or I'll eat this combination, which is chips and salsa. Okay, so this is SOP for E, right? That shows the combinations of inputs that I'll eat. Now, the reason why it's called sum of product is because if you were to take this as a base 10 equation, well, here's your products, and then you're summing them together. Now, this isn't a base 10 equation though, right? This is Boolean. So, you know, we're not multiplying here, we're anding, and we're not adding here, we're oring. Okay, but because of how it looks, if you did regard it as a base 10, that's where the term sum of products comes from. In fact, and is all often referred to as the logical multiply, and or is sometimes referred to as the logical summation, logical addition. But again, you're not really adding, you're oring, you're not really multiplying, you're anding. Okay? All right, so that's sum of products. The next thing is the next form, which is POS. Okay, POS is product of sums. Okay, and again, you'll see where that name comes from coming up. And we're going to come up with, okay, we're going to determine the product of sums for E. Okay, this is sum of products for E. Now we want to come up with POS, the product of sum for E. In order to do this, and I'm just going to tell you this at this point, but by the time we finish, hopefully you'll see the reason why. But just take my word for it that for now, to get the POS for E, we first have to start with the SOP for not. Okay, so we want to get the POS for E, but to do that, we have to start with the SOP for not. And again, you're going to see why coming up. Just believe me at this point. Okay, well, the way you get SOP for not E is you look at your truth table and you just write the terms for when E is 0. Right? Because again, not E is, I'm not eating that combination. So SOP for not E, it's going to have term not C, not E, not S, right? Because I won't eat that combination, or I won't eat not C, not G, S, or I won't eat C, G, oops, that's a G, not a 6. C, G, C, G, not S, Or I won't eat when we have all three, C, G, S. And keep an eye on what I'm doing here, because if I make a mistake, let me know. Sometimes it's easy to miss a bar. Okay, so this is my SOP for not eat. Okay, now, to get POS, the next thing we would do is we're gonna knot both sides of the equal sign. So I'm gonna knot this side and knot this side, right? If I knot both sides of an equal sign, I'm not changing anything. So what do you think this is gonna become? If you take a variable and you knot it twice, what do you think that equals? It just equals E, right? Because it's just like a double negative. So this is just gonna become E. Okay, now look at what we have on this side of the equal sign. We got this term, ORed with this term, ORed with this term, ORed with this term, the whole thing knotted. So if you consider this to be an input, right? Say this is like input A, and you consider this to be an input B, and you consider this to be an input C, and you consider this to be an input D. If you have 4 inputs being ORed together like this, and then the whole thing knotted, what kind of gate is that? If you're ORing thing and then you knot the whole thing, what is that? That's a NOR gate. NOR gate right here, right? Instead of 2 inputs, we got 4 inputs where the inputs are terms. So this equation right here is a NOR gate. The NOR gate equation where these terms are the inputs to the NOR gate. Well, what does De Morgan tell us about a NOR gate? What is it equal to? Yeah, a NOR gate, De Morgan tells us, right? One part of De Morgan tells us a NOR gate is the same as an AND gate with inverted inputs. So you see, I can take each input, right? Take C or not C, not G, not S. Take that input, invert it. Take this input, invert it. Take this input, invert it. Take this input, invert it, and AND them together. Okay, I took this NOR gate expression and using this part of De Morgan, I turned it into another expression that's equivalent. Right, because I took each input of this NOR, inverted it, and then I ANDed them together. Okay, now, we're not at the POS form yet. In fact, we have to do another step, but does everybody see how I got this? I'm just applying this part of De Morgan's. Okay, well now look at this expression. And just look at this term, okay? Don't look over here, just look at this term. If we just look at this term, it's input not C, ANDed with input not G, ANDed with input not S, the whole thing inverted. Right? And this term, input not C, ANDed with input not G, ANDed with S, the whole thing inverted. Well, what are these terms? What kind of gate is that if you're ANDing and then inverting the whole thing? Yeah, each term is an AND. And what do we know from De Morgan what an AND is equal to? Right, that's the other part of De Morgan, that an AND is equal to an OR with inverted inputs. So for each one of these terms, I can apply this part of De Morgan. So I take input C, invert it, which is just going to make it C, then OR it with the inversion of not G, which is just G, and then OR it with the inversion of not S, which is just S. Okay, then I do the same thing over here. It'd be C or G or not S. And same thing here. It'd be not C or with not G or with S. And I'm going to have to come on the other side of the the divider here, but this would be not C ORed with, not G ORed with, not S, and then these are all ORed together, or excuse me, they're all. Yeah, they're all, whoops. No, they're still ANDed because we're just applying, I'm sorry, yeah, these are still ANDed because we're just applying, or we're just applying the Morgans to these terms. So I'm ORing these, I'm inverting each input and then ORing them together, then these are still all ANDed together. So this would be equal to. So you see here, there's the NAND, so I'm inverting each of the inputs and then ORing them together, so. You know, this right here is this part of the Morgan, then I'm just repeating it for each term.
So it looks like in that final form, like within each product, right, you have that sum. And going back to the original truth table, like wherever that term is a 0, it's itself there, or wherever it's a 1, it's not itself. Is that true in general?
Right, that. And this is the reason why we had to start with the SOP for naughties, is because now, once we've done this derivation, once we've applied the Morgans twice, right, because we did this part of the Morgans here, and then this part of the Morgans for each of the terms here. Well, now, if you compare what we end up with, right, so if you compare this to what we started with, now we started with SOP for not E. So if you compare what we had here, what we started with, to what we ended up with, can you see a pattern of what happened? Because what happened? There's basically 3 things that happen. There's, oh, let's erase this here, because we didn't have this, right? We started with not E. Right, we started with this, it was not E for the SOP for not E, right? So we started with this, and then look, we ended up with E here. We started with not C, not G, not S. We end up with C, G, S. We started with not C, not G, S. We end up with C, G, not S. Right, so you see how all the variables are inverted, and then what else happens?
Products and sums.
Yeah, these products go to sum, these sums go to products. Okay, so you see, going back to this where I said, okay, if we want POS for E, we got to start with the SOP for not E. And the reason for that is because everything's going to invert. Right, if you started with SOP for E, you would end up with POS for not E. Okay, and you see the reason why this is called product of sums is because these terms are sums, right? They got the OR symbol, and then those terms are ANDed together, which, you know, again, you can think of as a logical multiplier. Again, if you were to view this as a base 10 equation, it would be product of sums. Okay. Now, you may be wondering at this point, you know, what's the big deal? Why are there these different forms? You know, why not just stick with one of them? Why have more than one? Well, the reason is, depending on your truth table, one of these forms could yield fewer terms, and the fewer terms you have, the smaller the logic circuit. Now, in this particular case, because we had an even number of 1s and 0s, you know, 4 zeros, 4 1s at our output, you know, the terms came out the same. So in this case, the logic circuits would be, you know, the same as far as number of gates. But knowing different forms of logic is handy because sometimes a form will yield less gates. Okay, and these aren't the only forms. Like I mentioned at the beginning, there's more than just SOP and POS, and not next class, but the class after that, we'll talk about a couple of additional forms. Okay. So I show this derivation to go from SOP to POS. I show it once, and what I expect is that you have an understanding of it, but once you have an understanding of it, it's okay just to go directly from SOP to POS by just inverting everything and changing ands to ors and ors to ands. Like, you don't have to do the derivation every time you do it, as long as you understand it. Okay, and when I did this derivation, I went from SOP to POS, but you can also go the other way. Like, if you have POS, you can get SOP by doing the same thing, by just inverting all the variables, including the output, and changing ands to ors and ors to ands. Okay, the most common error that people make when they're going either from SOP to POS or POS to SOP is when they invert all the inputs, but they forget to invert the output. Okay, the output also gets inverted too. Okay, I can't tell you how many times I've seen people, they'll have SOP for E, let's say, and, they do this, and then, again, they invert all the input variables, but then they just leave the output as E. Okay, which is correct, right? Because the output gets inverted too, okay? Okay, so let's see, where are we at? We're almost at the top of the hour. Well, let's do one more thing and then we'll take a break. The next thing we'll do is the circuit diagram for both SOP and POS. Okay, so first an SOP. All right, so let's look at this SOP equation right here, this one for E. You can see there's 4 terms. And if you look at each one of these terms, if the variable anded with the variable, anded with the variable. So what kind of gate do you think we need for that term? An AND gate, right? See, if we take an AND gate and we have input not C, input G, and input not S, well, out we'll get not C, G, not S. Right? So you see an AND gate will give us that term, and then for each of the terms, we'll have AND gate, 3 input AND gates. So this will have input not C, G, S. C, G, S. This, and we'll have C, not G, not S. This and for this term, be C, not G, S. So you see, for each one of these terms, we need an AND gate. And then these terms are all ORed together. So what gate are we going to need for that? Yeah, an OR gate. We just need one OR gate. Right? Outputs of all those ANDs goes to that OR gate. And that's where our output E is going to be. It's going to take this term and OR it with that term, and OR it with this term, and OR it with this term. Okay, so you see, an SOP equation is going to give you a logic diagram that has multiple AND gates, right? Because you need an AND gate per term, and then just a single OR gate. Okay, and that's true of any SOP equation, right? This is always true. This is the SOP diagram, right? It's always multiple AND gates and a single OR gate. Okay, well, if that made sense, then you should be able to tell me what a POS circuit would look like. Looking at our POS for E here, where we've got this term with inputs OR together, term with inputs OR together, inputs OR together, inputs OR together, and then they're all ANDed. So what would a POS circuit diagram look like?
The OR gates all fed into one AND gate.
Yeah, it should be opposite of this. Right, you're gonna have multiple OR gates, in this case 4, since there's 4 terms. These are all gonna be 3 input. right? 3 input, because there's 3 variables for each of the terms over there. Then, yeah, there's gonna be 1 AND gate. Right, because these all get ANDed together. Yeah, you can fill in the rest here. I mean, it's just the same as what we did up there, right? We just put the inputs based on the variables that you see in the equation there. Okay? So any questions about, anything up to this point? We got a little bit more to go. Timing diagram, black box, some Verilog code and min-max. I mean, this isn't gonna take very long, but because we're at almost the top of the hour, why don't we go ahead and take about a 5-minute break? And then when you come back, I'll finish this up. It'll probably only take about 15 minutes to finish up. And then once we're done with this, the rest of the class, you'll have to work on an activity. And then after the activity, you'll have some time to work on lab 0 to try to finish that. Remember, lab 0 is not due until Friday of next week. Okay, because we have the holiday. You all know about that, right? That Tuesday of next week is a Monday schedule because of the Monday holiday. Okay, just wanted to make sure, because there were people in my other section, they didn't know that. They were surprised, so. So anyway, let's take, like I said, about a 5-minute break. So, around 2 past, I'll start up again. Well, let's see. Here that, let's see, Joshua. Yeah, so on the, activity, if you have a green check mark, that means it's 100%. Like I talked about last class, when I grade the activities, I grade them on completeness. I don't grade them on accuracy because I give you the answers. So I just look to see that, there's work for each of the problems. And if there is, I put a check mark, which like I said, means 100%. If I find something missing, then I'll put like a certain number score out of 10. Is John Tracy's not here? There's one that way. I don't know if it's a water fountain or it might be one for, do you have like a water bottle? There should be one that way somewhere because the restroom's got. Yeah. So has any of your instructors been talking about the strike at all? What they're planning to do? What's the consensus?
Well, one of my professors, when asked if it was still happening, he said that the situation has gotten worse.
Well, yeah, that seems to be true from what I've seen in emails, but I don't know. Has anyone ever been on jury duty? You have?
Yeah.
Just the one time?
Yeah.
Did it actually go to trial? Did you actually have to sit there? Oh, oh,
No, I
Mm.
kind of want.
well, I've been selected for jury like 3 times, but out of the 3 times, only once did it actually go to trial. The other 2 times it got settled, and one of the times it got settled, literally they were gonna seat us. And they came in and said, okay, you can go home. They settled. Went up right to the last minute. So a lot of times that's what happens with these negotiations is, they'll go right to the 11th hour and then someone caves, So it'd be interesting to see, because I can't imagine the whole, there's 23 campuses. And I read somewhere that well, I guess it depends on the size of the campus. So it must be on average, but I read somewhere on average, they lose like $2 million a day when they close down a university like that. So if you've got 23,
Yeah,
that's like $50 million a day, 5 days, that's like $250 million. It would seem there'd be an incentive to settle, because what the chancellor's office supposedly has 12 billion in reserve. That's the thing that I can't get over. If there's like $12 billion just sitting somewhere, you know something
Yeah.
nasty is going on, you know, it's like, that you know corruption is happening. I'm gonna keep these $12 billion, I'm not gonna give it to anybody. You never know when it might rain. Yeah, I haven't decided what to do, but obviously, if, you know, it all happens, I'll have to cut stuff out of the course. But we'll see. I'm hoping they settle, so. Has any of the instructors said they're gonna hold class? Have you had any that said they're gonna
Yeah.
hold?
241 lab instructor.
Oh,
Yeah, he said he was pretty adamant. So,
okay. So there are some that are gonna. Has anyone bought tickets to like Cancun that week already?
my friends actually made that joke.
Oh.
Nobody didn't know it'd be like a week long. And the professor goes, "Oh yeah, I'm going to Cancun."
Well, that's the thing, is that even if, you know, that's the thing I was thinking about, even if I were to have class, I mean, I can't really require the students to be there, but I have to make it optional. I don't know, maybe I'll have just extended office hours. I'll just sit here and if you wanna come, go over homework, I'll be here. Cause that's the thing, if I run class, and let's say only half the people show, then that's not. Gonna screw stuff up. Any way you look at it, it's not good for anyone. Okay, well, that was about 5 minutes, so let's go ahead and finish up with these remaining forms of logic. And the next one is a timing diagram. And I have this example to show, you know, what this involves. Now, for this class, it's actually important to understand a timing diagram because this is how you're gonna verify whether your designs in Vivato work, right? Because you'll see that when you run the simulation of Vivato, it generates a timing diagram, and then you use that timing diagram to verify that you're getting the correct output for the various combinations of inputs, okay? And all a timing diagram is that it shows the values of your inputs and outputs versus time. And over on the left, that's always our t equal to 0. And then as you go left to right, time progresses. So here we have, you know, our salsa egg chip example. Here's the salsa input, the egg, the chips, and then we're gonna come up with what the E output would be. And all these inputs are starting at 0. And you can see that the S input is changing more frequently than the G and the S. And if you were to look at the values of our inputs as time progresses, you would see that right here, all inputs are 0. Then here, S is 1, G is 0, D is 0. Then here, only G is 1. Here, S and G are both 1, but C is 0. So as you go from left to right, in time, you would see that the combinations of inputs follows this truth table. Okay, so to come up with what the E output should be, we would just look during these intervals of the various combinations. Like during this interval of time, all the inputs are 0. So looking at our truth table, we should expect, right? We should expect that E would be 0. Right, because that's what E equals for that first input when all the inputs are 0. And then during this next block of time here, okay, during this block of time here, only S is 1. right? G and C are 0, so that's the second row of the truth table, so we would expect E to be a 0 also during that time. And then during this block of time, well, only G is a 1, right? The other two inputs are 0, so that would be this row of the truth table where E is 1, so we would expect to see E equal to 1. Okay, and then the next block of time, both eggs and salsa are both 1 and chips is 0, so again, E would be 1. Right, so you see E would be 0 up to here, then it would go to 1. Right, we would expect it to continue to be 1 for the next two inputs and then drop down to 0 for the next two. Okay, so the timing diagram just shows your truth table versus time, right? It's just like the truth table with, you know, time as a variable, if you will, right? With the inputs changing in time. Okay? So does anyone have a question about this? You're gonna get so much practice with timing diagrams in this class, because like I said, that's how you verify your designs on your basis board. Well, in Vivado, before you download to the basis board, you check to make sure you have the right simulation timing diagram that verifies that your design is giving you the truth table you expect. Okay? All right, so that's the timing diagram. Next thing, black box. As the name implies, the black box diagram is a black box or a box. So this is black box. Okay, so it's just a box. And the black box diagram, it just shows you your inputs and outputs. So for that appetite example that we've been using, and also you'll give your black box diagram some name. Like here, maybe I'll call it Gary _ app for appetite. Also, just to remind you, I mentioned this last class, Vivado does not like spaces and names. So whether it's a file name, a folder name, whatever you're using with Vivado, don't use spaces. You know, and like names of things, don't use spaces. Like typically people will use an underscore instead of a space. Okay, but the black box diagram, it's just going to show inputs on the left side and outputs on the right. So here, you know, we have C, G, and S, and on the output, we just have E. And sometimes they put the inputs like I show here, other times they'll do this. I mean, you can do either. Okay, sometimes people put the name within the box, sometimes they put it outside it. You can do either. Okay, so that's the black box diagram. The next thing, oh, system Verilog code. Okay, so you need to learn the syntax for writing like an SOP or a POS in System Verilog. So System Verilog is what we're using. There's also Verilog. Okay, most instructors that teach this class and also the follow-on class, CP 233, most instructors use System Verilog. But there is at least one instructor I know of that still uses Verilog. But the good news is that there isn't much difference between the two. There's probably like maybe a half dozen really like major differences. And the reason why they're so similar is because System Verilog is basically, you know, Verilog 2.0. You know, it's just the old Verilog with some enhancements, if you will. Okay, so, you know, if you take an instructor for CP 233, the follow-on class that's using Verilog, chances are the instructor will allow you to use System Verilog anyway. All right, but even if they didn't, it's very easy to learn the other one of these if you know one already. Because like I said, there's only like maybe a half dozen like real major differences. Okay. But anyway, we're going to use System Verilog, and to write a SOP equation, so we'll start with SOP. To write an SOP in System Verilog, you would start with a sign, and then you would put the output name, so say E in this case, and then the equal sign, And then if we were to write this SOP right here, well, in Verilog, you can't do a bar, okay, for a not. So what you use is you use the tilde symbol, right? The tilde is the squiggly line, the little squiggly line. If you look at your keyboard, you'd have to do a shift and then hit the upper left corner key. Hit the tilde like this, a little squiggly line. So to get that not C, we put the tilde, then the C. And then to and in System Verilog, you use the ampersand symbol. The ampersand, that's the symbol above the 7 on your keypad. So you'd have to do a shift 7. Ampersand kind of looks like this. Probably not the best ampersand, but again, you can look at your keys. It's the one above the 7, that symbol. So then we would and that with G. And then that's going to be anded with not S. So tilde S. And then the OR symbol in System Verilog, you don't use a plus because plus in System Verilog is actually add. So in System Verilog, to do an OR, it's the vertical line. So you have to do a shift and then hit the backslash. Okay, it's the vertical line above the backslash on your keypad or your keyboard. Right, so you see that's the OR, it's just a vertical line. All right, and then you just keep going, you know, be tilde, C, you know, ampersand, G, ampersand S, and then line again for OR, and you would just keep going. And then you have to end it with a semicolon. All right, so that would be POS in System Verilog, or excuse me, SOP in System Verilog. POS, you'd have a sign, an E, and like say if we were doing this one right here, this POS, it's just going to be C, or which is the vertical line, and then G with the vertical line, and then S, and then ampersand. You could put parentheses here if you wanted to just, you know, distinguish it. I don't think it's, actually, in this case, you might want to do parentheses, because I think if you don't have the parentheses, you could run into a problem here as far as, what you would call it, precedence. Like, I'm not sure if it takes and over or the other way around. So usually when I do a POS in System Verilog, I'll use the parentheses around the term. It may work without the parentheses, but I think the reason I use the parentheses is one time I learned that there was a problem, so. But anyway, you just continue on here, and then again, you gotta end it with a semicolon. Okay, so the main thing is that in System Verilog, not is a tilde, and is an ampersand, and or is a vertical line. Other than that, you basically write it as you would, you know, with the symbols. All right, the last thing here, unless there's questions before the activity, is there's 2 other forms called min, max, compact. And I saved this one for last because it's probably the least important of all these. In fact, the only reason I bring these 2 up is because there's an activity next class that uses this notation. All right, so it's really the only reason I bring it up. And like I said, it's not really something that's used a whole lot. But first, compact min. Okay, what that is there'll be a sigma symbol, and then after the sigma symbol, you'll have parentheses, and inside the parentheses are going to be numbers, and those numbers represent the indexes for the inputs where the ones are. So if we look at this truth table here for E, where the ones are when the inputs equal 2, 3, 4, and 5. Well, the compact min would have 2, 3, 4, 5 within the parentheses. It'd be like this. It'd be like E equals summation 2, 3, 4, 5. So that just means for input 2, 3, 4, 5, the output E is a 1. Okay, so compact min tells you where the ones are in the truth table. Okay, compact max . uses the capital pi. Now, is anybody really good at Greek letters? Is this capital pi or is there another name for capital pi? It's just capital pi. I've always wondered that. I've always thought there's some other name, but I guess not. I must be thinking of something else. All right, compact max, inside the parentheses, you put the indexes, the numbers for the inputs where the output is a zero. So you see in this table here, our output E is a zero for 0, 1, 6, and 7. Okay, so that's all it is. It's just a shorthand way to tell you or to inform you where the ones are and the zeros are in the truth table. Okay? All right, so that was all that I wanted to cover in class today. So the next thing for you to work on is I have an activity on this material. And like I said before, my answers are up on the whiteboard over there that you can check once you finish this. And, I would say that someone that does the activities conscientiously, what I mean by that is you really try to do it by yourself and then check against mine. And then if you have any questions, get your questions answered. It's a good way to prepare for the midterm. I would think that someone that's been conscientious doing the activities throughout the quarter, that when we get to midterm time, I would think that person would do well. Now, I can't guarantee that, but I would think that. Right, so I just mentioned that because, I would take these activities seriously, because even though I only graded on completeness, not accuracy, because again, I give you the answers and I allow you to help each other and all that, they're a good resource. Now, when you get the activity, you're gonna see that in the Boolean expression, I didn't do a bar or not, what I did was a little tick mark. Okay, the little tick mark is not. So for example, in that first problem where it has F equals U, V, tick mark, W, that's U, not V, W. All right, the next term is not U, V, W. Then the last term is not U, not V, not W. Okay, also, I'm gonna come around with another handout, but this handout doesn't have to do with the activity. This handout just has more information about the lab down criteria. Do you have to draw like a inverter or anything? If it's no, not in that case. I mean, if you started with just like ABC, then to get like not E is not C, you have to put in inverter. Okay. But here you're just going right away, like, it kind of implies that there's an inverter over here somewhere, but yeah, So for that first problem where it says also write the POS form, that's POS for F. So since you want POS for F, what are you gonna start with? SOP for not F.
So. TP will want to that one. Getting not that.
Yeah, show. Yeah, first show the SOP for no F and then show how we will. You don't have to show the De Morgan steps, but. Yeah,
That's it. Okay.
Yeah, I know some people can do it in their head.
No, yeah, just doing like the. Like working at the end. I like what I was just giving it out.
Right,
but
yeah,
just
but-
start off with that.
Yeah.
Yeah.